Okay, hello everyone. Good morning, good afternoon, and good evening. I'm Shah Faisal, and this webinar is organized by Professional and Education Activities Subcommittee, IEEE Power and Energy Society Young Professionals. Today, our respected guest speaker is Professor Sara Walker. She is professor at Newcastle University, United Kingdom. She is director of the Center for Energy and director of the EPSRC Hub on hydrogen integration for accelerated energy transitions and EPSRC Energy Demand Research Champion. And she is deputy director for the EPSRC Supergen Energy Networks Hub. She is an advisory committee member for the UK Energy Research Centre and the UK CCS Research Centre. She has experience in academia and also in industries. Today, she will talk about buildings as power plant. So please welcome Professor Sara for further discussion on the topic.
Thank you very much for the kind introduction. Welcome to the session today. I'm going to tell you a bit about some research we've been doing at Newcastle. And just to highlight that this is a bit of a team effort in terms of the research that was done. So whilst I'm presenting, just to highlight that colleagues Mohammed Royapour, Mehdi Pezouesh and Pete Davison all contributed to the research that I'm going to tell you about today. So building as a power plant was a project that came about partly because we had an opportunity with a brand new building at Newcastle University to think about how the building might enable us to do research using the building as a living lab. And so at the very early stage of the building being designed, researchers were involved to identify possible research projects that might come about so that the building designers could incorporate appropriate sensors, monitoring, data collection. So it's a really unique opportunity to then use the building once completed in order to do some research, which is what we've done. But why buildings? Why is this of interest? My background is in physics, and I've been looking at energy systems since moving into research and working across different energy uses. It's clear that buildings are a significant end user. So depending upon whether you're looking at just the UK or looking at Europe or looking at the whole globe, then it makes up a significant proportion of overall energy demand in terms of how we use buildings, and also a significant proportion of our carbon dioxide emissions. So doing something about buildings is important. And there's been a reasonable amount of work done looking at domestic buildings, but far less looking at commercial and industrial buildings. So that's why we were quite interested in looking at buildings. And then the other aspect which makes this highly relevant is the ways in which we expect decarbonisation to develop in terms of pressures that it puts on electricity systems moving forward. So in the UK, our electricity system is privatised and was the vast majority of it was built in the first half of the 20th century. So we have a fairly old electricity infrastructure in the UK. And that infrastructure is now needing to cope with increased electrification of different end uses as we decarbonise and move away from the use of oil and gas. We're also on our electricity system seeing significant amounts of renewable energy generation and also storage on the system, which wasn't there before when it was originally designed. And we're seeing different needs in terms of operational reliability, and part of that is to do with climate change and the different weather conditions that our electricity system will experience in the future. And in particular, something that we wanted to look at with this building example was how electricity infrastructure would cope with greater electrification of heating and greater use of electric vehicles in terms of the demand that the network would see. So that's part of the motivation for setting the project up. So to look at the building and think of the building potentially as a virtual power plant, then it's worth understanding the context of the building itself. So on the left-hand side is a circuit diagram showing the Urban Sciences building and how it's connected to the local 11 to 33 substation. So we have a building next to us called the Core. That's the one on the far left-hand side of the circuit diagram. And then the Urban Sciences building, and the electrical diagram shows that there's some solar photovoltaics as part of that connection, and an energy storage testbed. So I'll say a bit about that. The site that we are on also has an energy centre. That energy centre has a heat network that supplies some of the buildings on site. We're in quite a dense urban area that was a brownfield development, and so a heat network was really ideal for this site. The energy centre has also got a combined heat and power unit, so there's some electricity generation on site, and the energy centre is a 6 megawatt heat capacity currently and a 2 megawatt electrical capacity for that CHP unit. And right next to the building as well, we have a charging station for electric vehicles. It's got a number of fast chargers on there. So from an electrical network point of view, it's quite interesting because there's the loads on the site, there's generation on the site. And in terms of the building itself, which is shown on the right-hand side, then the building, the Urban Sciences building, because it was designed to be a bit of a living lab, there are some slightly more unusual bits inside the building as well, in that we've got part of the building that's direct current instead of alternating current, so we can see how internal circuitry losses behaviour. What's that like if it was DC rather than AC? And we've got some smart grid lab equipment in here. There's a transport lab. The building itself is home to our computing science school. So there's also a cyber incident room and smart cybersecurity lab as well. The energy storage testbed allows us to look at the behaviour of storage on the network and simulate different grid behaviours or circumstances, and to see how the storage behaves with that. But we've got the potential to link up thermal storage as well as electrical storage if we wish to. So the building has photovoltaics, it has heat pumps, it has thermal PV as well, so some photovoltaic panels that also have water circuits on them to keep them cool, and then we extract the heat from that water circuit. And as I said, the combined heat and power that's part of the overall site development that the building can connect to. So quite a versatile mix of technologies that we can look at as part of the building in terms of the research. So if we look at what we mean by a building as a power plant or a virtual power plant, then a definition that's out there in the literature talks about heterogeneous technologies. So we've definitely got that. We've got a big mix of technologies in terms of the buildings, in terms of the load in the building, but also in terms of some of the generation in the building or very close to the building. A mix of energy storage systems, including electric vehicles and controllable loads. Well, yes, we've got that. We've got energy storage within the building. And we've got electric vehicle charge points right outside in terms of connection to the local network. They're not connected to the building distribution board, but they're electrically wise, they're very close to us. Supported by information and communication technology to form the equivalent of a single virtual power plant. Yes, so the building has got a building energy management system, but it's got a lot of sensor technology and control technology that enables us to control the assets in such a way that we could potentially offer services to the local grid, and for all of those assets to be controlled in a combined and joined up way. And then another part of the definition is power and information should flow among the virtual PowerPoint stakeholders. So to an extent, we have that in the building. We've got the building occupants themselves in terms of the computing science team. We've got the labs and the lab technicians and the lab researchers, and we have the building manager. So there's ways in which we can approve mini projects happening in the building, inform the various stakeholders when things are going to be operating slightly differently, to enable them to know what we're doing in relation to the building. We've also been talking to some aggregator companies to talk about how the building might operate and offer services more widely than just to the university campus, from the point of view of reducing our load at peak times, going beyond the kind of boundary which is the university campus, and potentially offering that service to the local network through some kind of aggregation company to earn revenue from that behaviour. So we've got the essential ingredients that would meet the criteria of what is a virtual power plant. So this is what the building looks like. It's rather large in terms of its square meterage, and in terms of cost to build, it was about £58 million, of which about 12 million was over and above what would be a standard building energy management system and a standard university building. We've got some specific, very bespoke lab equipment on site, and like I say, a lot of sensor technology and centralized coordination of the data for that. Lots of additional meters as well, in order to enable us to monitor the performance of the building. So heat meters, electrical meters, water meters, gas meters. And that means that within the building, we've got nearly 16,000 data streams. Those data streams are going to a central repository, which we call the Urban Observatory, which is what that UO acronym is, Urban Observatory. And the building itself, in terms of the heating, ventilation and air conditioning elements of it, all of that is shown in that right-hand diagram. So using a building information model, we're able to show the schematics of all of the heating, ventilation and air conditioning installed in the building. So it's very heavily instrumented, and that was deliberate in order to enable us to do lots of interesting research on the behaviour of the building and its assets. So the building is split into roughly 3 areas, and it was designed specifically this way so that we could control bits of the building slightly separately. Core 3 is where all the staff offices are. Core 2 has got a lot of smaller teaching rooms and some of the IT labs, given that we're a computing science building. And Core 1 is where the large lecture theatres are. So you can imagine that The heating and ventilation requirements of these spaces are different for different times of the year, because some of the large lecture theatres are obviously only going to be used during term time when the students are in. Core 2 is a bit mixed. Some of our PhD students are in Core 2 and are in quite a lot, probably more than they should be. And then Core 3, where the staff are, is kind of an all year round as well. So we wanted to be able to control these spaces slightly differently, because we saw them being used slightly differently. Core 1 term time only, Core 2 and 3 all year round. And so that enabled us not only to think about control differently for those, but then to look at the performance of those and to identify how easy it was to control them differently, because they were going to have different uses. So the link to the Urban Observatory is shown here, and I've just took a screen grab of the model of the building that you can interrogate using the Urban Observatory interface. You can twist this graphic around, you can look at different levels. The red dots that you can see in places are where sensors are, and you can click on individual sensors and see live data for each sensor. But you can also download data for periods of time that you're interested in, and this is all open access. So if you happen to be interested in looking at some building data, we've got a whole load of it, perhaps too much. So it is the largest deposit of publicly held data in the UK. This isn't Urban Observatory doesn't just have the building. We've got traffic data, we've got air quality data, we've got weather stations, we've got other buildings on campus. So it's a huge amount of data going to the Urban Observatory. For the building itself, incoming values are recorded to 3 decimal places, and then that reading is only updated when there's a change. So it's not like we get lots of repetitive values. A way of saving on some of the huge memory requirement of all of this data is to only record when the data changes. But obviously, when it's saved to 3 decimal places, you can still get quite a lot of change. So as I said, with 15,800 data points in terms of meters, sensors, components, that's about, in a year, 50 billion data points. The work that I'm going to show you, we used about 1 billion data points. And because of the data only being recorded when there's a change in data, then you can see on the left-hand side how frequently some of this data changes. So the circulating pumps are the ones that change less frequently. And we have lighting data, so we're recording the light levels throughout the building, and that changes most frequently. But in terms of data, there's a really good range of the data types that we've got coming in, which tells us a lot about how the building is behaving. So then in terms of the data treatment, we do have to be a bit careful in recognizing that sometimes there's missing data or data streams that need cleaned up a little bit before we actually analyze them. And so with the data that we had, we wanted to treat any missing data, and we looked at some different approaches to do that. The one that seemed most appropriate is a method called K nearest neighbour, where you just vary the number of neighbours that you use, you vary the value of K, and 2 seemed to be the best approach in terms of accuracy of filling in that missing data. So most often you fill in missing data just by kind of taking an average. But when you might have a sensor that would normally be recording every 6 seconds and it's out for a whole day, then that's a lot of missing data to fill. So we looked at some different ways of doing this in order to try and identify the most accurate way of doing it. But with the missing data that we had, our error in the data was still less than 1%. So treating that data was good, but it was a small amount of data to treat, to be fair. So in terms of the loads that we looked at in the building and ways of controlling those in order to offer some opportunity for demand response, we looked at the different building assets. The building is heated. It's heated in two ways, so it's a bit weird to explain. But essentially, the building was built before the heat network was ready. Our building got planning permission before the energy centre. And so we knew that at some point we might want to connect to the heat network and have hot water coming into the building that we could then use for heating the space. So we've got 25 heat pumps, and those heat pumps take hot water and step it up from 40 degrees to 47 degrees in order to then have a secondary hot water circuit that's heating the spaces in the building. Because the heat network wasn't ready to provide that 40-degree water, we've actually got some gas boilers on site, and the gas boilers do the preheat for us. But electrically, we have 25 heat pumps that could offer demand response to the local electricity network. We've got a primary circuit of water that is taking that 40 degrees to each heat pump. And so there's circulating pumps on the primary side. And then once the heat pump steps up to 47, there's then water circulation around the spaces to warm them. And so we have a secondary circulation system as well with circulating pumps. So there's primary circulating pumps and secondary circulating pumps that also we could turn off in a demand response situation. We also have air handling units, so there's mechanical ventilation in the space. The windows do open, but there's also mechanical ventilation, and that mechanical ventilation ensures that carbon dioxide levels are kept below 1,000 parts per million, which is the guideline. And so potentially we could turn off the air handling units as long as the carbon dioxide stays below that 1,000 parts per million, and then we can offer demand response from the air handling units. And then the final load that we looked at was lighting. There's 22 lighting circuits that potentially could offer demand response, because we've always got the low-level emergency lighting circuits that could kick in if we wanted to turn down some of the lighting. But whilst the building's occupied, we don't want just the emergency lighting level. There are some minimums to ensure that we maintain from a health and safety executive guideline point of view. So making sure that the lux level stays at no less than 300 for a demand response event. So great, we did all this audit, we looked at the building, we looked at all these loads, and we identified what we could turn down. So this is what it looks like when you do a turn down event for the air handling unit. We've got a typical office and then a worst case office. So the left hand side is typical and the right hand side is worst case in terms of carbon dioxide levels that we achieved in that space. I'm sorry that the x-axis seemed to have gone a bit mad here in terms of the graph, but along the x-axis is the time units. And so what we looked at was to vary the number of occupants. So I should say that this is modelled data, not actual data, using Design Builder to model the building. Obviously, we had loads of data from the building to validate the model. So we modelled a certain number of occupants in the space. That's the brown line. So you can see for this typical office that the maximum occupancy was 25. And then we modelled turning the air handling units off. So the blue bars show when the air handling units are on. So they're on in the morning, and then we switch them off, modelled switching them off over lunchtime. And we looked at the response in terms of CO2 in parts per million, which is the black line. And so whilst there's no blue bars, the carbon dioxide level creeps up. And once it hits 1,000 parts per million, then you can't override the air handling unit anymore. It comes on in order to reduce the parts per million back down. So for the typical office, we didn't reach that 1,000 parts per million until the air handling unit had been off for 3.5 hours. The worst case on the right-hand side shows the air handling unit only being off for half an hour. So there's only one blue bar missing, a half-hour period. And then the carbon dioxide level shoots up past 1,000 parts per million, and the air handling unit has to kick back in. Also notice that the air handling units, when they come back on slightly boosted, so they're offering slightly higher air change rates in order to clear the air in the space. The worst case scenario room doesn't have openable windows, but if it did, then the heavy black dashed line shows what the CO2 would look like. So in that worst case space, we would be able to offer more demand response if the window was open, because we wouldn't get to 1,000 parts per million. But what this essentially shows us is we can offer demand response using the air handling units, and for most of the spaces, most of the typical office spaces, then we can offer 3.5 hours of demand response before the carbon dioxide levels get too high, and that is with the windows shut. So you can offer longer if the windows are open and providing that fresh air, instead of the air handling unit offering the fresh air. So we also then looked at the heating and cooling system and looked at what demand response might be possible using the heating and cooling system. So I've already mentioned that we've got this gas boiler injecting into the primary heat circuit at 40 degrees. And we've got a primary cooling loop as well, which is at just the incoming water temperature is 15 degrees for the cooling circuit. And so the heating and cooling primary circuits go through to a heat pump. The heat pump can operate in one direction to provide heating and steps up from 40 to 47. Or you can operate the heat pump in reverse and provide cooling and step down from 15 to 10 on your secondary circuit. So great, we've got 25 of these heat pumps along with the circulating pumps that could potentially offer cooling, could potentially offer demand response. So again, modelling the building, looking at winter time. So we looked at 5 heating months in the UK. Sadly, there's more than 5, but anyway, we looked at these 5. And we looked at, if we turn the heating off, turn off the heat pumps, turn off the circulating pumps, how quickly does the space cool down? How quickly do we have to then turn it back on again in order to keep comfort to an appropriate level? So the building set point is 21 degrees for heating. And thermal comfort standards produced by the industry say a thermal drift, i.e. temperature change, of no more than 0.5 degree per hour in order for comfort conditions to be maintained. So it's not just how much does it cool to, but it's how quickly does it cool that matters. And so we looked for each of these months, we looked at how the building behaved, and we've done a box plot here. So the values are the median, and then you've got the second and third quartile, and then first and fourth quartile in terms of the spread outside of the box plot. So on average, in terms of the building, we found over these months that the cooling only exceeded 0.5 degree an hour for 1% of the year, 1.2% of the year. So the building is performing really well. It's cooling down very slowly, and it gave us, in terms of demand response, the opportunity to offer demand response for up to 4 hours, no problem in terms of the extent to which the building cooled. We also found that once we switched the heating back on, then the building recovered quite quickly. So it recovered back to the 21 degree set point in about half the time of the demand response event. So if we offer demand response for 2 hours, we could recover the temperature back to its set point after an hour of the heating going back on. Now, this is a commercial building, and like many other commercial buildings, it's got a cooling load, not just a heating load. And so we looked at the performance of the heat pumps in reverse, offering cooling to the space, and what happens if we turn the cooling off. So when we looked at summertime and we looked at the drift in temperature and how quickly the building warmed up, we found that the building did warm up quicker than it cooled down. Summertime, in terms of temperature drift, we saw a temperature increase of 0.5 degree per hour happening about 14.5% of the time in these summer months that we looked at when there was cooling demand. Cooling was happening relatively slowly, but for some periods of the year, it was happening in terms of the warming up during the cooling period, warming up was happening faster than comfortable for over 14% of the cooling period that we looked at. So we can offer demand response in summer, but potentially for some spaces, or when external temperatures are particularly high, we might not be able to offer demand response because of this slightly faster warming up of the building. This building cost 58 million to build. Some of that is the extra sensors and so on. But in terms of the building itself, it is thermally, what we would call thermally heavy. It's quite slow to respond to external temperatures, which is great because potentially this enables us to use the slow thermal response of the building as essentially a storage mechanism to enable us to defer our heating or cooling electrical load for periods of time and help the local network. Our carbon dioxide demand response event potentially depends upon the nature of the space, but sometimes we can be offering demand response and recovering back the carbon dioxide levels fairly quickly. So we can get back below 1,000 parts per million after 15 minutes of the air handling units being back on, and to get back to whatever level it was before the demand response, about 45 minutes. So you can get back below the threshold, back below to whatever level it was before you started after about 45 minutes. And I mentioned those heating 1.2% of the year were slightly outside of comfort conditions, and for cooling, about 14.5% of the time were slightly outside of comfort conditions. So I did mention that we looked at other loads, and this shows some of that. So to mention the secondary cooling and the primary heating circuit, the circulation pumps and so on, then the heating pumps in terms of circulation are obviously, makes sense, more available in the winter months, less available in the summer. That's the red variation here. And then the cooling circuits are more available in the summer for demand response and less available in the winter. We did look at some demand response for the lifts, because we have a number of lifts in the building, so we could turn 3 of those off and still have enough lifts and offer some demand response there. We also looked at lighting. Lighting, not very seasonal, so tends to be available throughout the year. Air handling unit also available throughout the year. Heat pumps, you see less availability in spring and autumn when they're doing less cooling or heating, and then more availability in heating season, more availability in these peak cooling months as well. So a really interesting opportunity for load profile and for electrical load deferral throughout the year, based on the different loads, and also throughout the day and throughout the week. So we looked at availability, not just seasonally, but we looked at a weekly pattern and we looked at a daily pattern. So what that means in terms of the different loads. So remember, we said a virtual power plant should have heterogeneous loads. We've definitely got that. We've got lots of different categories of load, and the percentage contribution that they make to the overall building load varies. So that gives us some nice variety to the nature of the loads that we can defer. And essentially, of all of the electrical loads in the building, about half could offer some kind of demand response without interrupting the operation of the building and the thermal comfort of the occupants. We looked only at a maximum of a 4-hour demand response event. This was in line with guidelines from ASHRAE, which is the American Association for Building Services Engineers that set different various guidelines. So that was the maximum that we looked at. And as I said before, recovery time was about twice as fast as the thermal drift time. So that gives us an opportunity also to then think, how quickly could we offer a subsequent demand response event? So if we were asked to offer demand response and we did it for 4 hours, we'd need 2 hours before we could offer it again, because we'd need to wait for the building to get back up to comfort conditions before offering another demand response event. So the overall aggregated demand response loads for the building and the percentage load, it does vary ever so slightly throughout the year because of that seasonality of the heat pump load. So again, slightly less availability in the spring and the autumn periods when there's just less heating and cooling load, but getting up to 54% of overall building load being deferrable in July, and close to that 52% in December. So a really significant opportunity for the building to do something rather than simply be a passive load on the system. And this is just using the heating, ventilation and air conditioning components of the building. This isn't accounting for anything that the storage in the labs might do or different control strategies that we might use alongside some of the generation. So what that means is that there is always some load that the building can defer. We can always offer some demand response. And then depending upon the time of day and the time of year, then we can offer more. So if you wanted to be able to offer demand response for half of the year, then the amount of load we could defer would be a minimum of 99 kilowatt. So depending upon how much of the time you want to offer secure deferred load, then you can offer different amounts. So if you were only offering demand response at the 1% peak of your load, then we could get 226 kilowatts of load deferred, but only for 1% of the year, because there's only 1% of the year when the load is that high. The availability of deferrable load, I did mention something about within day as well. Here's a 24-hour day, so you can see that there's slight variation within day as well in terms of the availability of load for deferral events to happen. And this is the percentage rather than the absolute values. So office spaces are used year-round or used a little bit more often than some of the teaching spaces, which means that they're potentially available for deferrable load response, perhaps more often than some other spaces. And we wanted to do this and look at office spaces to extrapolate and think, how could this be generalized to other commercial buildings? Thinking about other ways to offer demand response, then if the building is behaving a little bit like a thermal battery, then what if we purchased a battery of the same size? What kind of performance could we get from that? So we did do a little bit of a comparison and said, what if it was a lithium-ion battery instead of the building electrical load that we were offering demand response for? So if we bought a lithium-ion battery that was the same size as the minimum load that the building can offer, either during office hours or out of office hours, but let's say out of office hours because it's the smallest, then buying a battery of the same size would cost us about 473k. This was done at 2019 prices. If you took the average deferrable load of the building throughout the year and bought a battery of the same size, then you're talking nearly $750,000. And then if you bought the battery that kind of gave you a really similar size to only being offering it for a quarter of the year, so the third quartile, only able to offer it about a quarter of the time, you're looking at 168 kilowatt equivalent battery would cost you about £1 million, which obviously is a lot cheaper than the £58 million building, but the £58 million building is there anyway and able to offer the same service essentially as buying a £1 million lithium-ion battery. So it just gives us an opportunity to think about what value could buildings bring to an electrical network if they have electrically heated systems, and how much would that save us in terms of storage that we would otherwise be purchasing. Is our building absolutely brilliant compared to the typical? Actually, no. So the USB, in terms of its energy consumption in kilowatt hours per year, is fairly close to an average good practice building. It's not absolute best spec possible. So it's fairly typical, and therefore we feel was a good case study to use to reflect typical behaviours of commercial office buildings. So I think that enables us to say that the building could, through controllable load, offer some behaviours that look like virtual power plants. So we did this work as part of an overall project looking at active buildings and what kind of characteristics made a building active. Excuse me. And so in terms of that project, we've been looking at building fabric and thinking about how to make buildings slow to respond to their environment, because it gives us that thermal battery behavior, that thermal response that we want. So trying as much as possible to include building fabric and passive design mechanisms so that buildings need as little heating as possible, and so that they do slow down or slow down in terms of their heating or cooling. We also want energy efficient systems, so whatever heating, ventilation and air conditioning is needed, that those systems are as efficient as possible. And we've got water-to-water heat pumps because they're on a primary water circuit and a secondary water circuit. And so heat pump performance of water-to-water heat pumps are around about 5 or 6 for a coefficient of performance. Air-to-water heat pumps, which are pretty typical for smaller commercial units, and for homes, they have coefficients of performance of between 2 and 3, depending upon the external temperature. It varies throughout the year. So we've got very energy efficient heating, ventilation and air conditioning design in the building. The other thing about active buildings that we thought was important as part of the design was to think about on-site renewable energy generation, so that the building could, if it wanted to offer demand response, could potentially be helping the network while still satisfying some of its own needs by having local generation. And so as part of the active building principles, we've been looking at different design of generation technologies and how to incorporate those better into the building. Active buildings could behave like thermal stores, but they could have other energy storage as part of the building. But that thermal storage really potentially here helps with mitigating peak demand, and potentially could then help networks to cope with greater electrification or greater intermittency of some of the renewable generation that it's starting to see on networks. We've also been investigating as part of the project what potential there is for electric vehicle integration and control as part of the virtual power plant. So if your electric vehicle at the building is plugged in, can it offer some demand response? Can it defer its charging? Could it actually discharge and contribute some electricity to the building or to the network to help at times of congestion on the network or constraint on the network? And all of that means that you need some kind of intelligent management. And the control strategy for that is something that we've also been investigating as part of the project at Newcastle University. So that covers everything that I wanted to say. I hope that leaves us some time for questions. Happy to take questions now and to open the floor to colleagues who are listening. Thanks.
Anyone have questions they can ask? You can write your questions and Anyone who question, they can write their questions.
If anyone thinks of questions after the event or wants to get in touch, then please drop me an email. So it's sarah.walker@newcastle.ac.uk. Sarah is spelt without an H. But yeah, please get in touch if you'd like to know more about the work we've been doing.
Oh, so until now, we don't have any question yet. But I think if someone asks, I can share with you.
Thank you for your comments, Sabina.
Okay, I can ask one question regarding the virtual power plant and integration of this building with like the national grid for cost optimization purpose.
Yeah, so our local substation is 11 to 33 kV. It's connected to the Northern Power Grid distribution network. At the moment, the way in which demand response works in the UK system is that is purchased by National Grid, and you have to be a fairly large load to offer demand response, or a very large battery to offer demand response. And so in the UK at the moment, given the size of the building, we can't currently bid into demand response markets on our own. But what we can do is use a company like Flexitricity, who are an aggregator, and they take loads that are dotted around the country that are too small to bid on their own, and they bid on their behalf as a grouping of loads. And so in practical terms at the moment, that is the only way in which we could be part of a demand response service, is through an aggregator to ensure that the total load offered as a demand response is large enough. But that's because at the moment it's purchased by National Grid as part of their frequency response service. Now, in the UK, we are seeing a development of the local networks at the distribution level for those companies to become system operators, not just network operators. And so there's potential that they might develop local markets for things like demand response to help with congestion on the network, to help with perhaps voltage constraints. And so whilst currently demand response is a global frequency market needing large demand response loads, in the future there's potential that our local network operator would want demand response, and that we would be significant enough to be able to bid directly into future local markets.
Oh, thank you. Anyone have questions, they can ask, or they can directly contact Professor Sara, which she mentioned her email ID. They can email also. No questions from anyone yet. There are no questions, and I'm very thankful to you, Professor Sara, for giving us time and sharing your fruitful knowledge with us. The topic is very interesting, and it can play a very good role in the future, and also it can improve the renewable energy integration in the future. And I'm also thankful to the audience who joined us and everyone who participated in this webinar with us. And thank you very much, Professor Sara, for giving us time, and hope to see you in future in different webinars and lectures. Thank you very much.
Thank you.
You're welcome.